Hello, everyone. It's great to be here again in this conference and have the great opportunity to tell you more about the TornadoVM project. But before I start, I'm going to motivate why we need something like TornadoVM. So heterogeneous hardware are pretty much everywhere: smartphones, tablets, laptops, data centers, and so on and so forth. Examples of heterogeneous hardware are not just GPUs. That's GPUs, FPGAs, RISC-V accelerators, AI accelerators, etc., etc. And well, this hardware is great because it helps developers to basically increase performance and decrease energy consumption. So in one way, to run workloads, a specific type of workloads, more efficiently. That's great, but how do we program them? How do we access them? How do we run tasks on them? Well, in this talk, I'm going to show you one possible approach through TornadoVM. So in a nutshell, TornadoVM is a Java parallel programming framework to run a subset of Java and accelerate those programs on GPUs, FPGAs, and multi-core systems. Sounds fun, right? OK, so what I'm going to do today, I'm going to start by a quick overview. So I was here in this conference showing you for the first time TornadoVM back in 2019. I'm not going to repeat the same talk, but I want to focus on what is new. And we have a lot of things going on in Tornado. So I'm going to do a quick recap just for you if someone doesn't know about TornadoVM. And then I'm going to focus on the main points. Like we have a brand new API, and we have a new set of features. And then I'm going to share with you our roadmap, basically what we're planning to do the rest of the year and the next year. And finally, what I'm going to do is to call what I call for action, basically points in which I identify that we can work together. OK, so TornadoVM, I already defined TornadoVM as a Java parallel programming framework, but it's also a plugin to OpenJDK, to JDK, that allow us to access where plain JDK cannot in a transparent manner. So with this combination, we can access a lot of hardware, a lot of heterogeneous hardware. So in a sense, TornadoVM cannot run by its own. It needs an existing JDK, OK? We call it TornadoVM. We call it VM because internally it has its own execution environment, data handler, scheduler, and so on and so forth. Right, so what's happening underneath of Tornado is that we employ different backends. Remember back in 2019, we have one backend, OpenCL. Now we have three. So the OpenCL one, OpenCL is a standard for GPU compute, well, for actually any type of accelerators. And there are a lot of vendors supporting OpenCL, including NVIDIA GPUs, FPGAs, RISC-V accelerators, Apple M2 chips, and so on. But we also have a CUDA PTX backend. We target PTX. PTX is the assembly code of CUDA programs. And the last backend we add is for SPV. So SPV is a binary representation for OpenCL. Can be used also for one API toolkit from Intel. Indeed, we use one of the APIs called Level 0 to dispatch those kernels. So with that, we can deploy Java on many platforms and use accelerators on many platforms, not just a GPU platform, but let's say a Jetson Nano with one GPU, with this IoT device for AI workloads, or a laptop, this laptop with a couple of GPUs, or a data center with FPGAs, and so on and so forth. So during the presentation, I'm going to show you details about all of this. And well, let's start with a demo. I'm going to show you first a demo. This is a typical computational photography example. It's a blur filter. It's typically now used in Zoom meetings when you want to blur your background, or typical filter in Instagram, TikTok, etc. What it does is it blurs some areas of the picture. I'm not going to go into the code right now, so if you're curious, it's online. But rather, I'm going to execute it directly. So I'm going to jump to the terminal. And first, what I'm going to do is to run a command in Tornado that will tell me which devices are accessible, which accelerators are accessible. I'm going to run this demo on my laptop. It's just a normal laptop with a couple of GPUs. So let's see what we get. So in Tornado, we have a command called tornado --devices. By the way, I put in Tornado here just because myself and our team is very lazy, so we are lazy. Tornado is just an alias to Java and a bunch of Java flags. That's all. So for Tornado itself, okay, A Tornado program is just a Java program that handles internally compilation and execution on entire environment, but it's just Java. Okay, so we have a command called dash devices, and if I run it, we have a bunch of information here. Let's see what we have. So first of all, this will tell us you have 3 drivers. Drivers means backends. You have 3 backends, and each is in different color, just to facilitate visualization here. Each backend has a set of devices attached to it. In this case, in this OpenCL backend, we have this one as default. Depending on your installation and your configuration, you will see as default a different one. Okay? In this case, I have this one. And this says OpenCL backend to use the NVIDIA RTX 2060. This is the NVIDIA GPU on this laptop. And we can access this device. So Tornado internally assigns an ID for each device. It's called device backend : device index. Okay? Again, depending on your installation and your configuration, you will see different reordering. The second the second device within the OpenCL backend is an Intel integrated graphics. This is an integrated graphics that is inside the CPU, and we can access through the OpenCL. And the last one is a multi-core system. So in TornadoVM, we focus on, of course, the big thing, GPU, FPGAs, because they are very esoteric. But you can also run on multi-core systems through OpenCL. The second backend appears to be SPV. And this one is running, or is going to run in the Intel integrated graphics. Okay, this device is exactly the same as this one, but accessible from different backends. This is interesting because in theory, we should get the same performance. But depending on the backend you target, because we have to deal with drivers, different implementers, and so on, you can get different performance. And the last backend that we see here is the PTX backend. And obviously, this is NVIDIA GPU with NVIDIA toolkit. We can access only, for now, an RTX 2060. Again, same device as this one, but accessible from different backends. OK, so enough about this. Let's run the application. I pass to my program a flag that says multi-thread, just for having a reference. So what I'm going to do is I'm going to run multiple times. Don't take this as a benchmark. Okay, this is a quick overview just to give you a flavor of Tornado. And when it's going to process, it's an image of 5,000 pixels by 4,000 pixels. Everything is on GitHub on the website that I told you about. And every iteration takes, with Java streams, around 8 seconds. Probably it's going to go down after a few iterations as soon as the JIT start compiling the whole code. But OK, let's say around 8 seconds. OK, and now the temperature is increasing, so I'm getting worse timers. But let's assume it's 8 seconds. So now, let's enable Tornado. I have a flag internally in my application to enable the Tornado pipeline. And let's run it. So if I don't specify anything, it's going to use the default device. Remember, it's the 2060 GPU. And interestingly, instead of 8 seconds, let's assume it's 8 seconds, we went down to 0.3 seconds. That's great. The first time takes a bit longer. That's because Tornado performs JIT compilation at that point, communicates with the driver, sends data back and forth, etc. It will set up the application. As soon as the application is set up, it will reuse the code and run it directly. You can say, well, Juan, I don't trust you. This is like magic. There's a black box. OK, I take that comment. So let's enable some debug info in TornadoVM to tell us in which device this application was executed. And it says it chooses the OpenCL backend with an RTX 2060. And we can change device. Let's say I pass a flag called device 01. If I go back to my list, 01 should be the Intel integrated graphics through OpenCL. So if I do that, and I run it, then I get the OpenCL backend and Intel integrated graphics. This device is less powerful than the RTX, the NVIDIA one, so it's a bit slower. Indeed, it takes 6 seconds the first time. Probably the second time will be a bit faster, 5 seconds. And just for the sake of the experiment, let's take also the SPV one that is going to be dispatched through one of the layers of Intel One API. And let me do that, so I can do 1, 0, sorry. If I do that, we notice that it's a bit faster. Indeed, it's around 50% faster than the OpenCL one. So the first time was around 4 seconds. Now going down to 3.6 seconds, right, to process such a big image. OK, this is just to give you a flavor. Let's go back to the presentation. So what do you expect? If I compare against Java sequential, and you may think, why do you compare with Java sequential? Well, I will explain the programming model later on, but essentially what the user does is to annotate sequential code. So that's why I compare it with Java sequential. You can get on this laptop up to 240x performance compared to Java. But more interestingly, if I compare with Java multi-threaded, using everything I can use on this laptop without using any external library, okay, I can get up to 30x performance compared to 16 CPU cores. Okay, now how this is implemented, how this is done. Let me show you details about this. So this is the software stack for TornadoVM. We have an API at the very top level. We don't detect parallelization. Tornado does not detect parallelization. It exploits parallelization. And here I show you the main key components of the API level. Our component is a task. Task means a method to run, a method to offload on the accelerator, on the GPU, on the FPGA, on the RISC-V accelerator, etc. We can create a group of tasks together that are going to be compiled in the same compilation unit to the same device and sent to the same device. And that's what we call a task graph. And around that, we build a task graph API. Tornado also offers to the user annotations. So in fact, we have two, add parallel and add reduce. And with that, we can cover at least the basic primitives in parallelism. And then we also have, or Tornado offers, what we call an execution plan. It's optional, but that gives you access to debugging information, task, dynamic task migration, etc. That's at the API level. Don't worry about those because I'm going to expand with an example step by step each of these blocks. Then at the runtime level, everything, in Tornado, everything happens at runtime, okay? So at the runtime level, we have a data flow analyzer. And basically, what it does is it will take this task graph and analyze data dependencies within the task graph. The reason for this, the main reason for this is that usually discrete GPUs don't share memory with the CPU. That means that even in Java, we have to pre-allocate data, send data via PCI Express, and then start the computation, and then send the data back. This is a slow operation compared to other components in the computing system. So if we can save some data transfers, we can increase the speed up overall. That's what we are interested to achieve. Tornado, from this optimized data flow graph, what it does is it generates its own bytecode. I'm not going to cover this. I covered this in the presentation back in 2019, so I refer to that. But I'm going to expand on the new components. We have the execution engine, which is the head of the compiler, basically the kernel of, the head of the TornadoVM. And internally it has an orchestrator, a scheduler, a device manager, memory handler, etc. And as you can imagine, also we have a JIT compiler. And in our case, we extend the Graal JIT compiler, and we have 3 JIT compilers, one for OpenCL code, OpenCL-C code, another one for assembly PTX code, and the last one for binary SPV code. Right. So let's start with API. We totally redesigned the API compared to the first time I came here. And when we redesigned the API, we ask ourselves the following question. First of all, how do we represent parallelism in a language that wasn't designed for parallel compute? So to do that, or to address this, what we do is to offer 2 solutions. First one is through annotations in the code. We have 2, add parallel and add reduce, Gary mentioned before. And this is a way to annotate sequential code, okay? And Tornado will do the magic to transform the sequential implementation or the sequential algorithm into a parallel code. This is suitable for non-experts because it doesn't require the developer to know the execution model or the programming model of the GPU or the FPGA, etc. But has some limitations, okay? There are some type of code that we cannot access or target. That's why we recently opened up a second API. And as the developers, you can choose one or the other. It doesn't matter for Tornado. And the second API is called the kernel API. And this is very similar to an OpenCL program or a CUDA program or one API program. Basically, it targets GPU experts or FPGA experts because it requires for the user the knowledge of the execution model and programming model for GPUs, for example. But those are complementary. As a developer, you can choose one or the other. So this is how we represent parallelization. The second point is how do we define, how we identify the methods to be offloaded to the GPU or to the FPGA. We do that through the task graph. And the task graph basically is an entity for us. It's an object that takes the input in and out that we need, plus the code to be accelerated. It could be methods from totally different classes. Okay? I will show you an example in a bit. And the last part is how we express some optimizations, how we interact with a debugger, how we do more advanced features. And we do that through an optimization plan. Let me show you. This is very abstract still. Let me show you with an example. I take typical matrix multiplication, widely used now in AI. It's perfect because it fits in one screen. So this is just Java. This is a Java class that contains one method, mxm. And this is the canonical implementation for matrix multiplication. There is nothing special in it. Now, the first thing that the user needs to do, if we use the loop parallel API, so annotations, is to identify which loops can run independently. So in the matrix multiply, the first two loops are totally independent. So that means that any iteration can run totally independent from the other, okay? Can be fully parallelizable. So the user adds these annotations. Okay, this is how we annotate the code by using the loop parallel API. But we can express the same kernel using, or the same algorithm using the kernel API. How do we do that? Well, if you know OpenCL, this will look very familiar to you. So we get the thread ID for each dimension. This is a 2D kernel that's going to run on the device, on the GPU, on the FPGA, etc. And we get the thread identifier for each dimension. And then we just do the final reduction. So this code will be dispatched n times, let's say. And for that, we need a grid of threads that the user will provide. I will explain you in a bit what it is. Right, so this is how we represent parallelization. Now let's identify the methods to offload. We do that, again, through the task graph. So a task graph is a way to identify data and code to be offloaded, and could be code from many different classes. So this API is very simple, actually. We have three main methods. Well, let's start with the constructor. We have a task graph. We pass a name, could be any name. It's a string. I put the S0, but you could do, full bar, whatever. This is useful at runtime if you want to change the device, for example, or to see the profiling information, because we will map with the name that you add. Then we have a method called transfer to device and another transfer to host. Again, usually accelerators don't share memory. So we have this concept of sending data back and forth. And remember, we have the matrix. We have A and B as an input, C as an output. So we pass A and B as an input, transferred from host to the device. Then we have a flag here that indicates what to do every time you execute the whole pipeline. We say, every time you execute this graph, send data every single time. This is useful if you have write-read data, for example. If you have read-only, you can use transfer mode first time only. Then we have a set of tasks. In this example, I want to simplify. We have one, but we can have many. And that's actually the beauty of this API. And in this case, the syntax is as follows. So we pass a name. Again, this is for profiler or for changing the device at runtime. And then we have a reference to an existing Java method. And this could be any point accessible from your class. And then we pass these data as any other function call. And then we transfer the results back to the host. So this is just an annotation part. This is just for identification. Nothing gets executed in the task graph. To do that, we need to create an execution plan. But to create an execution plan, since the task graph is mutable, meaning that at any point during runtime, we can append, add data and code, we need to freeze that. So we call snapshot. And then we have a type back called immutable task graph. So we say, you can do whatever you want with the task graph, but I need it in an immutable state, and then I can execute it. So we create an execution plan with the immutable task graph. And from the immutable task graph, from the execution plan, we can call many things. We can do warm-up phase, we can call the profiler, we can do dynamic reconfiguration. This is very cool. Dynamic reconfiguration means live task migration across accelerators during runtime, meaning that the TornadoVM can say, run for a while on GPU 1, and then later, TornadoVM realizes that GPU 2 is faster, so it migrates execution without restarting the application. You can enable that with this call. And then we call execute. Once we call execute, this is where everything happens. We compile the code, we manage the execution, we launch the application, and so on and so forth. Right, so this is everything I want to tell you today about the API. If you have more, if you're curious and you want to know more, we have a website for documentation, as also the TornadoVM project is open source and available on GitHub. Also, feel free to ask me later if you want. Let's talk about a little bit about the JIT compiler. So remember, we have annotations, task graph, and execution plans. And the only thing that the user needs to do is this transformation and these annotations in the sequence if we choose the loop parallel API. And then the user compiles with normal Java C. There's no modification in it, okay? Then the rest is runtime. We use Graal. So the first thing we do is we call Graal to say, give me the Graal IR representation, the intermediate representation, for each method that I want to offload. And then we start manipulating that graph. In a sense, the Tornado IR, the Tornado intermediate representation, is a superset of the Graal IR. We have a lot of new nodes, new compilation phases, and so on. We have a common IR across all backends, and then we specialize IR per backend. So the IR for PTX is different compared to OpenCL or SPV. In fact, there are different optimizations depending on the backend. After the code has been, or after the IR has been optimized, we have a lot of optimizations in which we interleave optimization of the Graal pipeline plus our optimizations. We generate the code. Let's say we choose SPV, the one on the right-hand side. So we generate SPV binary code, and then we dispatch that code through the corresponding low-level APIs. In this case, one of the APIs in one API called level 0. And we can compile the same method for different backends, right? Multiple times even. Right, so let's talk now about the key features that makes TornadoVM unique. One of them, I already mentioned, is the live task migration. It's the ability of Tornado to dynamically switch device to increase performance. We do that currently for performance, but we are working on also energy metrics. Imagine this. How cool is to say, Tornado, please switch to the device that consumes less energy? It's amazing. At the method level, well, this is not upstream yet. We are working on it. So how do we enable dynamic configuration? Well, with the code that I explained before, we have a couple of flags to say different policies. We say, for example, in this case, switch based on peak performance. So Tornado will warm up a little bit, will run on the device, and then we'll measure, and then we'll choose the best device based on peak performance. We also have other options like end-to-end, etc. If you're curious about this feature, we have a publication in 2019 about this. Check it out. Otherwise, you can ask me, of course, questions later. The second key feature of Tornado is that allows us to do batch processing. So you want to use GPU power or FPGA power because one of the big use cases is because you have big data applications. But big data mainly is because you process a lot of data. But these accelerators usually don't have that amount of memory. So what do? Well, we can say to the user, OK, do by yourself all this batching. But in Tornado, we enable this in an automatic manner. We say through the execution plan, we say use batches, we say with batch, and then we pass a size. And then TornadoVM automatically will batch this for you. Okay, this works well for 1D kernels, for example, if this type of code. The third feature I want to expand on, and I'm very excited about this, we released this 2 weeks ago, is the ability of running at the same time on many devices. Why not? The use case we have is the following. You have a bunch of tasks, a bunch of methods in the same task graph. But those tasks, those methods, don't depend on each other, right? They're totally independent. And in your setup, in your laptop or in your server, you have more than one accelerator. For example, a couple of GPUs, a GPU, and a FPGA. So why not map each task to different device? Tornado can do this in an automatic manner. This is upstream. And the goal is to increase performance. And this could be different devices. I mean, one could be an FPGA, the other one could be a GPU or a multi-core, right? For the TornadoVM runtime, actually, at that level, it doesn't matter at all. If you're curious about this feature, we have also a publication a couple of years ago in which we expand on how this is implemented and all the benchmark we implement. But feel free to ask me later as well. OK, one last thing, one of the key features I want to share with you as well is the ability to integrate Tornado into an existing Java project. So for Tornado, it's just Java. It's fully implemented in Java, except for the native part, in which we need to dispatch code through or to call to the drivers, okay, the CUDA driver or the One API driver, etc. But apart from that, the rest is Java, even the compiler and the runtime. So what we did was to integrate Tornado into a big data platform. We choose Flink. Flink is a streaming platform and has this architecture. You have at least 2 components, the job manager, which is the one that distributes data and code, and the task manager, which is everything will run in the task manager. So what we did was to integrate Tornado into the task manager level. The goal for us was to run and modify Flink applications on hardware accelerators. Okay, and we did it. We have a publication coming this year. We have also a blog post. It's a lighter version of that publication, if you're interested, in which we talk about the challenges to do this. There are many challenges that we faced, especially with data manipulation, and the solutions that we propose. OK, so what's next? I talked about how TornadoVM is until now. Now I'm going to expand on what we are planning to do, and I'm very excited to share this with you. The first thing is that it seems like we're missing an opportunity because, OK, at the beginning I showed you an example of matrix multiplication in Java, but who's going to implement matrix multiplication in Java? I mean, we have this vendor from CUDA, NVIDIA, AMD, Intel that gives you very fast libraries for linear algebra, deep learning. Why are you going to implement this in Java? Well, the reason is, for one side, you don't want to do it because you want to be flexible, you want to be portable, you want to reuse code, etc. But it usually offers lower performance because those libraries have been optimized by experts during many, many years. So it seems like we're missing an opportunity here. On the other side, just using pre-built libraries, well, they are very vendor locked in. It's not easy portable. You just one specific device, probably with one specific set of parameters. But they are really, really fast. The question is, how or what if we combine these two? Is it possible? Well, the answer is yes. This is ongoing work. And let me show you how. Let's take the matrix multiplication I talked about. And let's imagine we don't have any pre-built library calls. So this is how we do it, right? I already explained this before. We have a task graph. We have a task. And we have a reference to an existing Java method, Java code. And it's coded in Java. What we did was not introduce any new types. What we did was to introduce just a specialized task type. It's called library task. And in this case, I'm saying call a library from the one MKL suite, is the Intel One API math kernel library function called sgem. Okay. And that's how we do it. And you can say, well, Juan, you just call a native function in Java. What's the big deal? Wait. What if we combine these two in the same graph? That's the deal. Let me show you a use case. You load data from a database. Let's say you use a prebuild function library. You can do it in Java, but let's assume that you use a prebuild function library. And you load the data. And then you have a phase in which you manipulate that data. You could use Tornado as it is to offload those kernels of initialization. And then you have in the same graph a third call in which you call, let's say, a CUDA function for deep learning. Everything is in the same task graph. That's the deal, right? And our use cases could be deep learning, AI, math libraries, function, et cetera, et cetera. We have a prototype working, and indeed, I'm going to show you some benchmarks about this. So what I did was to execute, I think it was in this laptop, yes, the sgen function from one API, from Intel library. The first metric I show you here is what Tornado can achieve without calling a native library. And you have different input sizes, and the bar shows speedups against Java sequential. So the higher, the better. And as you can see, in Tornado right now, and with an Intel integrated graphics, you can get 25, more than 25x performance. Not that bad for integrated GPU. What if we call the specialized function? Well, instead of 26x performance, we get 500 times faster. So it's a gap of 24 times x performance that we are losing if we don't do this, right? And everything is implemented in Java in the same task graph. That's the beauty of it. Okay, second thing is in our roadmap, and we have prototypes about this. It's coming very soon, by the way, is to integrate with Panama. And let me motivate why we need this. So Tornado, as well as Apache or other frameworks, they have a couple of issues. First of all, if data is on heap, they have to copy on heap data to off heap and then launch the kernel because memory is not shared. It's not really an issue, it's a performance issue. You can think, okay, fair enough. The second one is more challenging. Is that in order to invoke the kernel, because they have separate spaces, the GC must be locked. Otherwise, we might risk into the GC coming in and moving data while the GPU application is running. We don't want that. So Tornado, as well as Apache, other frameworks, we lock the GC. And in order to avoid that, we go through Panama to offer off-heap data structures. I think that's the way to go. Another idea we have explored is the following. What if, that sounds crazy, what if we have the Java heap or a subset of the Java heap as a unified space between the CPU and the GPU? We share pointers. So there is no need to marshal or to send data in different spaces, and the GC will work. Well, we work with 4 modifications, actually. If you're interested, that could be a totally separate talk. But if you're interested, we have a publication coming this year. Just in a nutshell, we don't go through this solution because it will require more changes in JDK, and especially in the GC. It's much simpler, and in my opinion, right now, much cleaner to go through Panama. So that's why we're going through Panama. How will it look like once we integrate to Panama? Well, remember our expression here. This is a typical vector addition with Tornado. Instead of using a primitive float array, we will use something like float array class that Tornado will offer you. And internally, that will allocate a segment. And the beauty of it is that that segment, we could pin that pointer into shared memory or unified memory between the GPU and the CPU, et cetera, right? And the ultimate goal for us is to combine this with the hybrid API I talked about. Why? Because data will flow naturally across JIT compile task and library calls. And that's, I believe, where a lot of speed is going to be there. OK, cool. Is Tornado enough? Is this enough? Well, I don't think so. There are many things in Tornado to improve. And I'm going to do a call for action, actually, with a set of things I'd consider how to improve this. One of these is I would like a tighter collaboration with the Graal JIT team. Why is this? Because, well, we base on Graal compiler. We try to catch up with Graal as soon as there is a new release. I know Graal is open source, but once the change is done, it's done, right? So what we like to do is to be more involved with them somehow. I propose something like special interest groups, and the reason I propose this is because we are already doing something similar with Intel. So we are collaborating with Intel in 2 special interest groups, one for one API language specification, the other one is for one API hardware group. That gives us kind of an insight about the immediate kind of year roadmap, and then we can plan ahead within our team. And I believe this is not just useful for Tornado, this is useful for anyone that uses Graal, which I believe there are a lot of people now. The second point I want to mention, and I'm glad Gary mentioned this before, is that now that you have Panama, you have, in my opinion, a huge opportunity to define new types for AI and heterogeneous systems. For example, ND arrays, tensors, half floats, and so on and so forth. What I would like to see is that a standard definition of types, and then each vendor can implement those types accordingly. For example, if you have an ND array, which is kind of, if you like, the tensor representation, a generic tensor representation for AI, then Tornado could do, for example, share memory on that ND array. Another vendor could do different things. And I believe, again, this is not just useful for Tornado, but other frameworks, deep nets, for example, is pure Java for AI, and so on, will benefit from this. The last point I want to mention, this is just more a discussion. Let's imagine the future. What it will take, something like Tornado, I'm talking about Tornado, but it could be something else, like HAT that Gary mentioned before, to be included in Java, in the Java platform. Well, I believe that perhaps the JVM spec should be modified somehow. For example, I'm thinking about math precisions. The GPU operations, for example, they operate in the same spec as IEEE 754, if I remember correctly. It's the same as Java. Okay, but GPU vendors and FPGA vendors usually gives you a faster way to do fast math. Okay, and this is especially useful for AI. So how this accommodates with Java, I don't have an answer for that. It's just something that I throw here. I think you do something similar for the vector API, accommodating FMA operations. I think we might have something like that. One possible way to implement this is just something that comes to my mind. Again, this is open for discussion. I like the Linku approach. Linked from Microsoft, although it's for database, there are some works that use those APIs for GPU compute. And what I would like to see is a kind of a nested execution environment. Tornado is something like that, actually, that can offer you some kind of, specific, for a specific type of workloads, an environment for that. Let's say AI environment, HPC environment, heterogeneous environment, FPGA environment, and so on. Again, those are generic ideas. We can discuss it. With that, I'm going to conclude. So today, I show you TornadoVM. I hope I convinced you. It's a platform to run applications, a subset of Java, at least, on heterogeneous hardware. And this does not include only GPUs, but also FPGAs, RISC-V accelerators, multi-core systems, and so on and so forth. We focus on Java, although we have experiments running TornadoVM through other languages like Python, R, Node.js. If you're curious, I can point some demos that we have online as well. Today, I also discuss key features of Tornado. For example, in my opinion, live task migration is amazing. Remember, it's the ability of Tornado to change devices during runtime. Batch processing, multi-backend support, and multi-device concurrently. Interaction with other frameworks like Apache Flink, etc. I also share with you the roadmap that we're planning, especially this hybrid API and integration with Panama, and some points for call for action. And with that, I conclude my presentation, and I'm happy to take questions. Thank you very much.
So if you do these library calls, can you understand me?
Can you speak up, because it's a bit difficult.
Okay.
Can you speak up? Yeah.
If you do these library calls, does TornadoVM has to translate your data from Java to off-heap memory and to corresponding format that the library expects? So does Tornado have to know the library, the external library you call?
Right. The experiments we have, we do on-heap to off-heap, right? This is just for experiment. So everything is in Java. In the future, what we want to do is to integrate with Panama. Still, it's going to be Java, but data will flow, let's say, in a seamless way between a task that is going to be compiled at runtime and a library call. So there's no distinction between them. Yeah, go ahead.
Nice presentation. If a data set is being operated on read, modify, write, is that something you support?
Read, modify, write. So you're planning to have a specific kernel in mind?
I'm doing a relaxation on a large irregular surface, and I want it to be smoother, and I want to iterate until it's smooth enough. But I don't want to make a new array every time I
no, it's reused. Yeah, okay, good point. It's reused. Yeah. So yes. You can have the same expression, and then Tornado will cache depending on if it's read only or read write, and then we'll send automatically data when it's needed. But that's annotated in the task graph level.
Okay, so you do that. So in-place algorithms, good. That's very natural in GPUs. But my next question is, how does that interact with the auto-segmenting? If my graph is too big and the framework needs to break it down, how does it keep appropriate versions of the segmented version, the segments of the data set alive, so that they can so that you don't clobber, you don't relax one section before you use the previous data as input to neighboring cells in a different section?
Yeah, I'm not sure I catch the question, but essentially, not sure if this is implemented now in Tornado. There will be a way through batch processing, for example, right? If the data cannot fit there. But it's up to the user what it needs to know, the capacity that can run on the device. What we do is to go usually full capacity, and then we adapt.
So the auto-segmenting works if every cell is read any number of times or written once, even written multiple times. But the auto-segmenting breaks down with read, modify, write bulk operations. So I was wondering how you address that issue.
Yeah, I don't have a clear answer for that. We can discuss later. Yes. Okay. Thank you very much.